Welcome back. Today we're going to talk about hyperbolas. Now, hyperbolas are another one of these conic sections that we've been looking at. And what you're going to see is, again, these spatial relationships and the ability to associate certain distances in these figures is going to help us in the understanding of how do all these equations work and how do I graph these and how do I evaluate them. So here we go. As we look at a hyperbola, it can be either vertical or horizontal. And so what we're gonna do is just draw a general diagram here. Let me grab my pen. Come on. There we go. And so this is going to be what's called the focal axis, and these words are going to seem familiar to you. And so what we know about the focal axis is there are foci on these axes. So here's one and here's one. And our hyperbola is going to have a center as well. So here's my center. And what does the focus actually, or sorry, the hyperbola actually look like? Well, it looks like this. It's kind of like two sideways parabolas, right? So a hyperbola could go this way, or it could be up and down, like this. So it can be vertical or horizontal. And the distances here are going to look very, very familiar. I want you to check out these things. The focus, think about this for a second. In the figures that we've been talking about, the focus is c distance away. Well, the cool part about this is these are still c away from the center. So you start at that center. If this is at 0, 0, right? So it's going to be c on this side and c on the other side for my focus. And my vertices, what's pretty cool is my vertices are going to be at a, and negative a is 0. Now, granted, if we move the center around, right, to hk, it's going to be a different, like, h plus or minus a, that kind of a setup. But it's a distance away from the center. And we're going to have a couple of significant lines in here. So my hyperbola is going to have these two lines here that define these vertical lines in this case. And this is going to be x negative a, and this is going to be at x equals a. And the way that a hyperbola works and the way that you draw it is there's some defining lines, and I'm going to draw them in and then explain to you how they work. I'm going to draw them in pink. There's a big X here that actually goes through the center. Okay, and this box here that's defined, so here are the four corners of this box, and stick with me, you're probably like, what is this box? What is he drawing? What is going on? This box here has this principle applied to it, that these distances on top and bottom make it a rectangle. And so you'll notice I've got the distance c here and the distance a. Well, b is this distance here. It's from the center to the outside of this box. Well, what is this box actually? Well, this box actually defines the asymptotes that this hyperbola goes in between. And so if this hyperbola continued, it would follow along these dotted pink lines. I want you to look at an example here. Let me pull up my graph here. So here I've got a hyperbola, so check it out. So we haven't even talked about the general equation, but just look at this parabola for a second. I've got x squared over 4 minus y squared over 16 equals 1. And I've picked these two lines, not arbitrarily. We're going to talk about what exactly the relationship is. But I'm going to turn these on, and I want you to take a look. Check this out. So you can see, I'm going to zoom out, and look what happens. As they go into infinity, the hyperbola gets closer and closer to these. That's the definition of this asymptote, right? Well, those asymptotes are going to be defined by this equation. Asymptote. Y equals b over a times x. And this one over here is y equals negative b over a times x. That's why the distance b is important. Distance b is important, along with a, defines the slope of these asymptote lines. Okay? And so my x equals a lines and x equals negative a, that distance. And then my b distances gives me the corners. Well, think about it like this for a second. Slope is rise over run, correct? So if I go up b and over a, there's my slope, right? So up b over a. Or if I go down b over a, this would be like a negative b distance, down b over a, that's the slope of this asymptote line. Keeping that principle in mind, those are my a, b, and c distances in a hyperbola. My equations can look like this. X squared over y squared, not y squared, a squared minus y squared over b squared equals 1. Kind of like an ellipse, they're equal to 1. Or it could be y squared over a squared is equal to minus, not equal to, minus x squared over b squared equals 1. Check out my equation here. There's an x squared, and look at which way it goes. That axis, so the focal axis is the x-axis here. There are two axes, the transverse axes. Transverse axis is vertex to vertex. And my conjugate axis is 2b, like the length of 2b, and it's perpendicular to transverse. It doesn't touch the hyperbola at all. Let's go through some of the traits of these hyperbolas by sketching a graph first. So when we've got a hyperbola, it could look like this. And so I'm going to go ahead and draw in my asymptotes right away. And the standard equation for a hyperbola that goes this way is the standard equation for one that opens like this. So we've got our two portions of the graph that cross the x-axis. Standard equation is going to start with an x. So it's going to be x squared over a squared minus y squared over b squared equals 1. And so our focal axis is going to be the one that goes through both vertices and the foci. So that's going to be the x-axis. And it's a reminder that y equals 0 on that one, because that's going to become significant when we start to move around that center point. My foci are left and right the distance c, right? So the distance c is to the foci. So plus or minus c, 0. My vertices are plus or minus a, 0. My semi-transverse axis, my transverse axis is the one that goes through the vertices. So the length of half of that axis is a. The length of half of the semi-conjugate axis, remember that's b. Pythagorean relation for this one is c squared equals a squared plus b squared. And I've got these transverse axes to help me with that. Y equals plus or minus b over a times x. What follows from this, excuse me, I'm going to sneeze. I'm not sure. I guess I don't have to. So I thought I did. When I move this around, say I put the center up here at HK. Center H comma K. My standard equation looks exactly the same with the modifications for the center. H goes with x, k goes with y. So my focal axis, instead of being y equals 0, it's y equals k, because my focal axis just gets moved up from y equals 0 to y equals k. My foci are h comma k with the addition of c. My vertices are h comma k with the addition of a in there. That's how those coordinates change. Semi-transverse is still a, this is still b. Pythagorean relation is the same. And actually, these are going to be the same throughout, so you can fill in that part of your chart. My asymptotes have to take into account the fact that I have b over a, but I've moved my x and I've also moved my y. So it's over a certain amount and up a certain amount. The next two take into account the fact that this graph can also be oriented the other way. So now, as you'll notice, my transverse axis is no longer side to side. My transverse axis is up and down. It's vertical, which also means that my focal axis is vertical. And I'm kind of getting ahead of myself. But when this is the case, A and B stay the same. So A is on the bottom first, B squared is on the bottom second, and my x and my y are simply going to shift places. So my foci are going to be 0 plus or minus c because they are now on this y-axis, right? And my vertices are going to change because they're going to be vertical from my center. All of these are the same, but what changes is instead of it being b over a, now it's a over b times x, so plus or minus a over b times x. If I move it in the coordinate plane, up this way, let's say, and my center is at hk, my standard equation changes in the way that you probably predicted it would change. Y minus k squared over a squared minus x minus h squared over b squared equals 1. So now my focal axis, think about this for a second, my focal axis is this one, whoops, this one here. So it's x equals h, and it has to be because if my y-axis is x equals 0. So then my foci are h comma k, but I have to take into account the fact that it's plus or minus c. And my vertices are h comma k, but I have to take into account that there's an adjustment of a. All of these are the same. Down here it changes as you would expect, plus or minus a over b times, and this is x minus h plus k. Everything is shifted around, and I've kind of breezed through these a little bit quickly because they're based on the same principles that we've used in the previous two sections to talk about where are these values. A mental note: if you can draw a picture, sketch a graph, and you can look at these physical relationships of how far is A, what does that mean? It goes to the vertices. How far is C? It goes to the foci. Those are going to help you very, very effectively solve these problems. Find the vertices and the foci of the hyperbola 4x squared minus 9y squared equals 36. It's got a minus, so feasibly it is a hyperbola, but it needs to be equal to 1, so I'm going to divide by 36. So I've got 4x squared over 36 minus 9y squared over 36 is equal to 1, and this would be x squared over 9 minus y squared over 6, no, 4. Here I am going and taking a square root when I shouldn't be. Equals 1. So this is a squared, this is b squared. So a equals, b equals, c equals. A is now 3. B is 2, which means if my Pythagorean relationship is used, it's 13, so C is equal to the square root of 13. Therefore, my vertices, what does this one look like? If x is first, right, it looks like this. So if x is first, then that means my hyperbola goes this way, which means that my vertices and my foci are manipulating the x coordinate, right? So my foci are on the x coordinate. All right, so on the next one, here's what we're going to do. We're going to take these pieces of information and find an equation of the hyperbola with the foci of 0, -3, and 0, 3, whose conjugate axis has a length of 4. And their suggestion is that we sketch it first. So let's make the sketch first, and that's going to help us identify what values we have and what values we need. I've got these foci. I'm going to draw those in. And they're at 0, -3, and 0, 3. So that tells me that I've got a hyperbola that actually opens up this way, right? And so my hyperbola opens up this way, and that's going to help me establish the form of my equation. So when I've got this hyperbola, and I can put in my x's and my y's now. So it goes this way, so that means y squared is first. The fact that this distance right here and this distance here are the same means they're equidistant from 0. So my center is at 0. So it's 3 up, 3 down. And so that means that I'm not going to have any changes in my center. So I don't have to put in parentheses. So on the bottom, I've got to find my A values and my B values. So let's look here. My foci tell me that my C value is 3, because that's the distance from the center to the focus. With my conjugate axis, that's going to establish my B distance. Okay, so if my conjugate axis is 4, that means that each side is B. So that means B is 2. And if I use my Pythagorean identity, C squared equals B squared plus A squared. So 9 equals 4, which is B squared plus A squared. So 5 is equal to A squared. 5 equals A squared. And so A is equal to square root of 5. What does that make my, what does that make my equation? So A goes first. So this is going to be root 5 squared on the bottom. So I've got y squared over 5 minus x squared over b squared, which is 4, equals 1. That's my equation. All right, let's do one more. Find the standard form of the equation for the hyperbola whose transverse axis has endpoints -2, -1, and 8, -1, and whose conjugate axis has a length of 8. Here's what I'm going to do. 1, 2, 3, 4, 5, 6, 7, 8. -1, -1. Here is my transverse axis. What that tells me is the ends of my transverse axis, those are my vertices. So the total length of that is 2 times the value A. The center is halfway between those. So if it's from -2 to 8, that's a total of 10, right? So 5, 1, 2, 3, 4, 5. Down here, so my center is at 3, -1, because that's halfway between. My A value is 5, because that's half of 10. So here's 5, here's 5. B equals, C equals. My conjugate axis has a length of 8, and so my semi-conjugate axis, or half of that, would be 4. And so if I do A squared plus B squared equals C squared, which is my Pythagorean relationship, I've got 25 plus 16 is equal to C squared. So C is equal to the square root of 41. What do I need to do? I need to find the standard form of the equation. It's crossing my x-axis, so my x comes first, and my center is at 3, -1, so I've got x minus 3 squared, accounting for the fact that the center is moved, over a squared, which is 25, minus y plus 1 squared over 16 equals 1. That's all there is to it, guys. So thanks for watching, and we'll see you next time.